Hello, and welcome to Chapter 3, Section 2, Part 2. So we are continuing on with our exploration of correlation and linear regression. So first, before I continue, I done goofed. In the last video, I said for the interpretation of a residual, I left out a key phrase. My bad. So really all I'm adding to it is this part right here. So when your x variable, whatever that is, and then whatever the x number is. So basically we're saying when x equals this, then the predicted y value is however much higher or lower than observed. So I just wanted you to add that back into your notes, and then we move on. So today we talk about the coefficient of determination. So last time we talked about correlation coefficient, and now we have the coefficient of determination. They sound very similar. They are also related. So the correlation coefficient is what we talked about last time. That's R. So coefficient of determination is R squared. Basically, R squared is a number that talks about how accurate our regression line is going to be at making predictions. So you know how R, the correlation coefficient, was always a number between -1 to 1? Then R squared, if you square that number, you're always going to get a number between 0 and 1, positive, because when you square something, it always ends up positive. So the coefficient of determination, R squared, since it's always going to be a number between 0 and 1, we kind of talk about it in terms of percents. So because we're trying to describe how accurate our regression line is going to be, we can kind of use like, it's going to be this accurate, this percentage accuracy. So we can say like this percent of our dependent variable or y variable can be predicted without error from the x variable. So basically we want that percentage to be higher, because if you have a higher percentage, you're being more accurate with your predictions without error. So if you also think about what you started out with for R, our correlation coefficient, if R was a number that was closer to 1 or closer to -1, that means it was stronger in its relation to how close it was to a line. So, or your scatter plot was close to a line. So if you are squaring a number that's closer to 1 or -1, you're going to get a number that's closer to 1 when you square it. So 1 being like 100%. So if you had a distribution of values in your data set that was perfectly on a line, so R equals 1 or -1, when you square it, you get 1. So that would mean 100% of the y variable can be predicted without error from the x variable, which makes sense, because if all your data points fall exactly on a line, then your equation for that line of best fit should be the best possible to make any other predictions. And so that makes sense that way. So if you're ever asked to interpret your coefficient of determination or interpret R squared, the most common wording you'll see on the AP test is going to sound like this for the interpretation. Blank percent, so whatever number you get for R squared, percent of the variation in whatever your y variable is, so insert the problem here, can be explained by the least squares regression line relating y on x, or y to x. So if we're talking about, for example, a data set that was talking about, I think last class we talked about the lean body mass and the metabolic rate. So then whatever percent of the variation in the metabolic rate can be explained by the least squares regression line relating the metabolic rate to the lean body mass. So in that sentence, the variation's pretty much talking about like your prediction without error. Another number we want to talk about that relates to how accurate our predictions are is called the standard deviation of the residuals. So standard deviation, if you think back to when we first started talking about standard deviation, is basically like the distance, the average distance away from the mean. But this time, since we're talking about our residuals, we're basically looking at like a list or our data set of all of the residuals that we have based on our scatter plot. So out of all those residuals, what is the standard deviation? So what's your like average residual, and what's the average distance away from that average residual? So the formula for the standard deviation of the residuals looks like this. And you don't actually have to calculate it a whole bunch. More so it'll be given to you in a problem, and you will need to know what it means though. So because it's a standard deviation being that average distance, then a higher number for your standard deviation of the residuals would mean that your residuals are more spread out, which is not really great, because if you have a higher standard deviation, more spread means that your predictions are going to be less consistent. So a smaller standard deviation of the residuals is better, because this would make our regression line a little bit more accurate, because all our residuals are going to be closer to, or sorry, all of our observations and our predictions are going to be closer together. So the interpretation of the standard deviation of the residuals would basically sound like this. When using the least squares regression line with our x variable to predict the y variable, we will typically be off by, and then whatever you get for your standard deviation of the residuals number. So when we use that word typically, it's basically saying like on average. Sometimes the problem you're given will be given in terms of computer output instead of our usual like calculate everything ourselves. So instead of giving you data, you'll be given something like a computer printout, sometimes it's called. It'll look like this. Sometimes it's referred to minitab. So minitab is a computer program that actually does basically what our calculator does, just it can handle more numbers. It's like an actual program that statisticians use. Because our graphing calculator can only handle so much. They're trying to fit all this programming into a small device, and so the memory, storage space, and all of that is smaller. But minitab itself basically does what we need to do in statistics. So we want to be able to read what their printouts look like as well, because this is also how you would see it on the AP test. So looking at their printout, this is about a problem where we took data from 15 high school students, their foot length and their height was measured and recorded. So they're basically trying to predict what their height is from their foot length. And so you can see in the problem here, on the left here, it says foot length. So that basically tells you what the x variable is. And it'll always usually say in the printout itself, like the x variable. It does not, however, tell you the y variable in the printout. So that one, read in the problem for what the y variable is going to be. Okay, but right above the x variable, it'll always say constant. So if you think about math terms, constant means like that y-intercept, the number you would add in an equation. So for us, that refers to the a value, the y-intercept. So the number right next to constant, right here, this is your a value. The one right underneath it is going to be the slope of our regression line, so b. Because, you know, we usually write our equation as y equals a plus bx. So with the printout, that first column, those two numbers, highly important. Then you'll also see s underneath our x variable. So s we talked about, that's our standard deviation of the residuals. So it even says s equals. Then RSQ right next to it is r squared. So they give it to you as a percent. Sometimes you'll see it as a decimal, but usually it's a percent. So they've already turned it into a percent for you. So they're basically saying the r squared value here is 0.486 or 48.6%, which if you think back to like what you want r to be, you want it to be close to 100%. This is actually not that good. R squared of 50%, not that great. It's like very medium. Next to it, there's this RSQADJ, like adjusted. We don't look at that one. Just ignore it. And then all these numbers over here, we also don't need just yet. You won't see these numbers again until chapter 12. So really, the only numbers you need are like in the first two columns. So for this particular problem, if we were to write out their least squares regression line, or the equation for it, it would look like this. Y hat equals 103.41 for our a value, plus 2.7469 for our slope of x. So Of course, when we write our least squares regression equation, we always need to define our variables. So in this case, x would be that foot length. And then based on the explanation of this problem, y would be our predicted height in centimeters. Okay, since they gave us r squared, that means we can also find r. So if we know r, if we square r, we would get r squared, then the square root of r squared would give us r. So one thing you do need to notice though is every time you square root something, your answer is always going to be positive. But r can be both a positive and a negative number, so you actually have to pay attention to the slope in your equation. Is your slope negative or positive? So for us in this case, our slope was positive, telling us that r is going to be positive. But if your slope in the equation is negative, that means you have to make sure that you make r negative. So it's not like a automatic thing when you square root r squared. So of course in our calculator we can't square root a percentage, so we have to turn our 48.6% into a decimal of 0.486, square root that, and then that will give you r. So our correlation coefficient here is 0.697, which is decent, moderate, because we want r to be close to 1 or -1, and here it's kind of close to 1. So moderate, which kind of makes sense too because our r squared wasn't great either, so moderate. If we were to interpret this correlation number, we can say that the relationship between foot length and height is positive because of the positive slope and moderately linear. Remember, our correlation number always talks about how linear it is, so we have no idea if this data set is actually curved or not. We wouldn't be able to tell that unless we were able to see the scatter plot of all our data points, which we don't have here. And then the last piece of information that we had was that the standard deviation of the residuals, S, was 7.95. So if we were to interpret that in context of this problem, we would say that when we're using the least squares regression line with foot length to predict height, we will typically be off by 7.95 centimeters, because that's the unit that we were using to measure everything here. So the last thing I want to talk about in this section is calculating the least squares regression line using means. So fun fact, the least squares regression line, that line of best fit, always passes through the mean of the x variable and the mean of the y variable as a coordinate. So as like x bar comma y bar, because remember x bar and y bar with the bar on top means the mean. So knowing that, we can calculate our a and b values using just the means of the x and y variables, the standard deviations of the x and y variables, and r, our correlation coefficient. So if we have those 5 pieces of information, we can calculate the slope and y-intercept of our least squares regression line. So for example, kind of the same example as before, but we've got the 15 high school students. We're going to try to predict their height using their foot length. So it's given to us that the mean and standard deviation of foot lengths are 24.76 centimeters and 2.71 centimeters respectively. So in case you didn't know, respectively just means it lists the numbers in order of which they listed the words before. So mean comes first, then standard deviation. So I can write that out as the x bar is 24.76 and the standard deviation of the x variable is 2.71. So then they said the mean and standard deviation of height, which is our y variable, is 171.43 centimeters and the standard deviation is 10.69 centimeters. Okay, so then lastly they say the correlation is 0.697. So using this, we can also figure out our least squares regression line equation by using the 2 formulas from above. So if we know to find b using r times the standard deviation of y over the standard deviation of our x variable, then we would have the 0.697 from r times our standard deviation of y, which was 10.69, divided by 2.71. Calculating that out, I get 2.75, and so then I can use that to calculate my a, my slope. So the formula is y bar minus b times x bar. So that would give me y bar is my mean of the heights, which is 171.43, minus the b value that I got earlier, which was a 2.75, times the mean of the x variable, so 24.76. And calculating that out, I get 103.34. So writing out my full equation, then I have, and I'll use the other method of writing now. So I'm going to define my variables within the equation itself. So the predicted height is equal to 103.34, that was A, plus B was 2.75 times X, which was our foot length. So just a reminder, every time you write out the equation, you have to define your variables, either this way or to write out, or actually spell out what x equals and y equals. And that's it. So if you have those 5 pieces of information, you're always able to find the least squares regression line equation. And that's it for the chapter. Thanks for watching. Have a great day.